Welcome, this is Dr. Plague, and today we'll take a quick look at how to create a clock signal suitable for the Intel 8088 processor. It is recommended that you use an 8284A clock generator IC, but what if you don't have one? Is all hope lost? Absolutely not. You can easily generate your own clock signal. In this video, we're going to look at a few different ways to generate an appropriate clock for the 8088. And be sure to watch until the end where I'll show a one-chip solution to get both a processor clock and a peripheral clock. Now, I do happen to have an old Intel 8284A, so we'll take a look at that first, and we'll power it up to examine its output. Then we'll do some experimenting to see how we can recreate a nearly identical signal. So please stick around, and I'll see you right after this. So, first of all, what is so special about the clock signal required for the 8088, and why is it recommended to use a specific clock generator IC? According to the 8088 datasheet, the clock needs to have a 33% duty cycle.
What's a 33% duty cycle?
If you take the clock signal and look at one period of it, which is the shortest section of time that repeats, then the percentage of time that the signal is high is the duty cycle. So, in this case, we have a 50% duty cycle since the signal is high for approximately 50% of the full period. A 33% duty cycle would look something like this, and it would keep repeating.
This is boring. Carry on.
So, do we really need exactly 33%? Probably not, but we should respect the minimum low and high clock times in the datasheet. That means if we run the 8088 at a slow enough clock speed, then we might be able to get away with a 50% duty cycle. But regardless, let's just stick with 33%. So first, let's take a look at the recommended 8284A clock IC. I'll provide power and ground. I'm going to use 5 volts for power. I'll ground the C-Sync and the 2 address enables. And I'll pull the reset in high. Now I want to pull the frequency / crystal select line high so we can use a TTL level clock signal on the external frequency or EFI pin. Now we can send any duty cycle clock signal to the EFI pin to get a 33% duty cycle out of the processor clock pin. I'm going to use a waveform generator to create the input clock signal. But if you don't have one and you have an 8284 chip to play with, then you can refer back to my video called Fun with the 555 Timer to create your own input clock signal. Now let's wire this up and take a look at the output. I'll connect the waveform generator to pin 14 and I'll probe that with the first channel of the oscilloscope. I'll also connect pin 8 to the second channel of the oscilloscope. I'll set the power supply to 5 volts. The 8284A will generate a processor clock that is 1/3 of the input frequency. So I'll set up the waveform generator to give us a square wave at 3 kHz. This should give us a 33% duty cycle output clock at 1 kilohertz. And notice that if we trigger on the second channel, that's exactly what we get. I'll take some measurements and notice that it is a 33% duty cycle. Now let's try some different duty cycles on the input and see if it affects the output. I'll try 20% duty cycle, and the output looks fine. Now let's try 80% duty cycle, and notice that the output still remains at 33% duty cycle. Perfect. Now let's see if we can figure out how to do this without the 8284A. Notice that what we are trying to do is to divide the frequency by 3. So if we use the input clock to start counting from 0 to 1, then 2, and repeat 0, 1, 2, then we're getting close. Let's write this sequence out in binary. If we take a look at either digit, then you can see we essentially have a 33% clock signal. So let's go into DigitalWorks and find a binary counter. I'll select the 74HCT161. Now, before you do this in DigitalWorks, make sure you check out my previous video on the 74HC161 and 163 errata, or else your simulations may not work. I'll include a link in the description below. To get this IC to count, we need to make sure the master reset, count enable input, count enable carry input, and the parallel enable input are all high. Then I'll send our clock into the clock input pin. I'll place a couple LEDs on the 2 least significant counter outputs. And we'll add them along with the clock to the logic history. Now, if we simulate this, it's going to count from 0 to 3 before repeating. But we want to repeat after counting to 2. So how can we do this? This chip has a master reset pin that we want to bring low when the count gets past 2. So when the count first reaches 3, then we want to reset the chip so that we're back to 0 instead of 3. We can use a NAND gate to do this. When the count is 3, which is the input to the NAND gate, then the output of the NAND gate will be low. So let's try this out. And now we count from 0, 1, 2, and back to 0, 1, 2, etc. We can use bit 1 of our output as our processor clock signal. Beautiful! By the way, we don't want to use bit 0 for the processor clock, and I'll explain why a little later. Now, unfortunately, I don't have any 74HCT161s, but what I do have are some 74HCT163s. The difference is that the 163 has a synchronous reset, meaning that it will only reset during a positive going clock pulse. So let's replace the 161 with the 163. Notice that it counts up to 3 instead of 2. This is because it doesn't reset when reaching 3 until the clock goes high. So now we want to reset after counting to 2 instead of 3. Now we can use bit 1 of the output to reset the chip, since it only goes high after we've reached 2. But I want to send it through an inverter since a low resets the chip. Now, if we simulate this and look at the logic history, we'll see a 33% duty cycle output. Great! Let's try this on a breadboard. I'll wire it up just like how we had it in DigitalWorks. I'll use an inverter from a 74HCT04 hex inverter IC. Pin 1 will be the input to the inverter, and pin 2 will be the output. I'm going to place a 100K pull-down resistor on the clock input so we're not floating when the waveform generator is turned off. And notice that we really do get a 33% duty cycle clock signal out of it. And if we adjust the input duty cycle, the output remains at 33%. Excellent. Now let's take a look at a different IC. I'm going to use a 74 series 393 chip, which is a dual 4-bit binary ripple counter. Just like the 161, this chip has an asynchronous reset, but it's active high. So instead of using a NAND gate like we did with the 161, we can use an AND gate. There are 2 ripple counters in this chip, and we're going to use the first one for generating the processor clock. The input clock goes to pin 1, the reset is on pin 2, and the 2 least significant outputs are on pins 3 and 4, which are bits 0 and 1 respectively. So I'll send pins 3 and 4 into an AND gate and send the output of that gate to pin 2. I'll use bit 1 as our processor clock output. Now, if we simulate this and look at our logic history, we'll see a 33% duty cycle output. Okay, let's go back to the 8284A and notice that pin 2 gives us a peripheral clock, which is half the frequency of the processor clock, and it has a 50% duty cycle. So now, channel 1 is showing the processor clock, and channel 2 is showing the peripheral clock. Let's go back to the 393 chip and see if we can use the second ripple counter to generate the peripheral clock. Let's use the processor clock as the input to the second ripple counter, which is on pin 13. I'm going to ground the reset on the second ripple counter, which is pin 12. This will keep the counter counting. Now, let's use the least significant bit on the second ripple counter as our peripheral clock. Let's simulate this. And notice that the peripheral clock is looking good. Now, let's breadboard this up and look at it on the scope. I'm going to use the 74HCT08 for our AND gate. Pins 1 and 2 will be the input to the AND gate, and pin 3 will be the output. Again, the first channel is the processor clock, and the second channel is the peripheral clock. Now, you might notice that the peripheral clock changes states during the negative edge of the processor clock, and this might bother some of you. So if we look at the logic history of both least significant bits of the first ripple counter, you'll see that they both look like 33% duty cycle signals. And the negative going edge of bit 0 lines up with the positive edge of bit 1. So you might be tempted to think that we can use bit 0 to clock the second ripple counter, so that the peripheral clock changes states during the positive edge of the processor clock. Let's try it. It doesn't work. The peripheral clock is no longer 50% duty cycle, and it's not at half frequency. What happened? This might look like a bug in DigitalWorks, so let's try this on the breadboard. And we get the same result. So this is not a bug in DigitalWorks. But why is it doing this? The answer is that we're not just counting from 0 to 2, but rather we're counting from 0 to 3. But the counter resets immediately when it reaches 3, so we don't see the 3. But if we zoom into the least significant bit, then we can see that it does spike up a little when it reaches 3. This is why we can't use the least significant bit to drive the second ripple counter. And remember, with the 161, I said we couldn't use the least significant bit for the processor clock? Again, this is the reason why. But let's look back at the output from the 8284A and notice that its peripheral clock transitions on the negative edge of the processor clock. So we're good using bit 1. Now, instead of using a waveform generator, I'm going to wire up a 14.31818 MHz oscillator. Notice that if we divide that by 3, then we get 4.77 megahertz, which is the speed that the original IBM PC 5150 ran at. Also, notice that if we divide that by 4, then we get 3.579545 megahertz, which just happens to be the color burst frequency for the NTSC composite video signal. If you've ever wondered why the IBM PC ran at 4.77 megahertz, then that could give you a clue. Anyway, I'm going to send the output of the oscillator into the clock input of the first ripple counter. And let's take a look at this on the scope. It doesn't quite look like it's 33% duty cycle, so let's measure it. We find that it's actually about a 38 or 39% duty cycle. But we just need to make sure that we respect the timing requirements in the 8088 datasheet, which says we need a minimum of 69 nanoseconds for the high time and 118 nanoseconds for the low time. And we have about 80 to 82 nanoseconds for the high and 128 to 130 nanoseconds for the low time, so we're good. Now, just for fun, let's connect the oscillator up to the 8284A and see if it still maintains a 33% duty cycle. And look at that! Its duty cycle is now 36%, which is also higher than 33%, similar to our own circuit. Notice that our solutions so far have had 2 ICs. Let's see if we can get both the processor clock and the peripheral clock with just 1 IC. I'm going to go back to the 74 series 163 chip, but this should also work with the 161 if you happen to have that chip. Both chips should work because we're no longer going to use the master reset pin, which is the only difference between the two. One is synchronous and the other is asynchronous. I'm just going to tie the reset high. To get this IC to count, we need to make sure the count enable input, count enable carry input, and the parallel enable input are also high. and then we send the clock to pin 2. But I want to make sure this counter counts from 6 to 8, and you'll see why in a little bit. To get this counter to start at 6, I'm going to use the parallel load functionality to load in a 6. That means I'll set the data inputs to a 6, which are pins 3, 4, 5, and 6. I want them to be 0, 1, 1, 0 respectively, which is ground, 5 volts, and ground respectively. Bit 2 on the output will be high when the count is 6 and 7, but will go low when the count reaches 8. Therefore, we can use bit 2 to load a 6 back into the counter after it counts up to 8. Remember, the load function is synchronous, so it needs a positive clock pulse to load a value. Therefore, the 8 will remain active for a full input clock period. So let's disconnect the parallel enable input from 5 volts and instead connect it to bit 2 of the output. Now, if we simulate this, you can see we have a one-chip solution for a 33% duty cycle processor clock coming out of bit 0. Let's see if we can also get a peripheral clock out of the same single chip. Notice that once we count up to 8, the most significant bit is now high, and we can send that into the most significant bit of the data input pins instead of having it grounded. Now the value of 14 is loaded into the counter. And now we count from 14 to 15, and when we get to 16, we don't have a fifth bit to represent that, so the counter just rolls back over to 0. Now bit 2 is 0, which loads another value into the counter, and since bit 3 is also 0, we load in a 6. And the loaded value keeps toggling back and forth from 6 to 14. Now, bit 3 gives us our peripheral clock, and we've only used one chip. Fantastic! Let's wire this up on a breadboard and test it out. You will notice that we can send in any duty cycle input clock to get a 33% duty cycle clock on the output. We also have a peripheral clock. And guess what? If we add in the 14.31818 megahertz oscillator, and measure the duty cycle, you'll see we are right at about 33 or 34%. This is because we're loading a value synchronously with the counting of the counter. We've outdone the 8284A. Beautiful! I'll be using this clock circuit in future 8088 videos. Now, bear in mind that if you use this circuit, you'll probably want to keep the processor in reset while the oscillator stabilizes. And you could probably accomplish this with a simple RC circuit going through a Schmitt-Traeger inverter such as a 74 Series 14. Now that you've seen some ideas on how to create a proper 8088 clock, I'm sure you could think of some other ways of doing that same thing. I hope you've found this video useful, and if you've liked it, then please peck at that like button. And please subscribe if you haven't already done so.
Hey, great job making a clock with one IC.
Wow, thank you.
But I have a question.
What's that?
How do you tell time with this clock? Also, how do you set the current time? But most importantly, what's a 33% duty cycle?
I've had enough.
Hey, where are you going? You haven't answered my questions. I'm so confused.